Okay, please take a seat. Also the last arrivals. At the moment, it's not possible to register. So if you didn't, Neven, if you didn't register, just sit down, enjoy the beginning. And those who didn't register yet, they will be able to register at coffee break or lunch break, okay? Okay. Good morning. Welcome to GASPISA. I'm Bianca Poggianti, if you don't know me, and it's a pleasure for me on behalf of the Scientific Organizing Committee and the Local Organizing Committee to welcome you here in Pisa for this conference. Here you can find the names of the organizers, and I just will give you a brief introduction to the meeting, just a few scientific words, and then lots of logistics. So as you saw in the rationale, the focus of the meeting are really the physical processes that shape the stellar and gas histories of galaxies. The emphasis we wanted to give, the organizers wanted to give, is really on the physics, not only on the demographics, on describing what is happening, but what kind of conclusions can we draw about the physics. The conference is divided in three main sessions: stars, gas, and environment. But obviously there are, it's a division that doesn't make much sense because everything is intertwined. So it's just for, organization. There is no real separation. And we will tackle different scales, different redshifts, different environments. So we are here really a variegated pool of researchers coming from different perspectives. So I think the success of this meeting will depend on how much we are willing to learn from each other and to contrast what we think we know with what the others think they know from a different perspective. So the three main questions of the meeting are these ones. So how do different physical mechanisms regulate gas inflows and outflows? And what are the effects on the star formation? What drives, in general, the star formation activity in galaxies from the clump scale to the galactic scale? And what processes determine the properties of the galaxy populations as a function of environment? The meeting is organized. There will be reviews, 25+5, targeted and regular talks, 15+5, short talks, 10+3. And we have 2 poster sessions. You see the posters, that there are some more that needs to be hanged here, so everybody has the occasion to see them anytime. There will be short talks from the posters, and there are 3 discussion sessions, which I hope will be lovely and participated by everybody, led by a panel with SOC and LOC members. Okay, if we needed an excuse to do this meeting, which we don't obviously, there are many excuses. It's 460 years from Galileo's birth. Galileo was born here in Pisa. It's the year of celebration from the 850 years of the Leaning Tower. There are many occasions, many things in town. And it's 5 years and 70 papers now of the ERC gas program, which officially ends this Friday, so the last day of the conference. GASP is, allow me to just tell you what it is a program that is financed by the European Commission as part of an ERC advanced grant. And GASP stands for Gas Stripping Phenomena in Galaxies, and is based on a MUSE ESO-Large program, the first MUSE ESO-Large program, and a number of multi-wavelengths follow-ups, HST, ALMA, Meerkat, JVLA, lots of things that you can read there. The questions we addressed are quite similar, of course, to the ones of this conference, which is where, how, and why is gas removed from galaxies, and what is the effect on the galaxy star formation history. We studied 114 galaxies, redshift 0.04, 0.07, stellar masses in the range 10 to the 9, 10 to the 11.5, and in different environments, clusters, groups, filaments, and isolated. Although 2/3 of the gas sample is in clusters, as I will tell you in a moment. The selection was particular, so we selected disky disturbed galaxies with signs of extraplanar debris in the B-band images, plus a control sample of normal disky galaxies. Okay. And this is the list of people, and more importantly, these are the faces of the people. Many of these people, you will see them here, helping you at the registration, bringing the microphones, helping you around. So this is one in the list of meetings that we had. Allow me just a few words on GASP. You will not hear all the GASP results in this meeting, but I want to point you, if in case after the meeting you want to look for something, where to look for these results. So GASP has shown essentially how the integral field spectroscopy plus the multi-wavelength data set can help, can really be a way to identify different physical mechanisms, different processes at work. But keep in mind that the GASP selection is biased, so GASP cannot be used, and we couldn't use it to study, in general, a census of the physical processes in different environments. Okay. So we had both field galaxies, a third, as I said, and cluster galaxies. And for clusters galaxies, probably GASP will be mostly remembered for the so-called jellyfish galaxies, or anyway, run pressure stripping, where we really, I think, let me say we killed it, if I allow me this. The multi-wavelength study is really fundamental. This is an example of one galaxy where we had, different, many different wavelengths. And the most important thing for us was the coverage, especially the MUSE, because the other things had the same and even bigger coverage. The MUSE coverage that goes at least out to 7 effective radii. The resolution, MUSE, ALMA, and so on, was only 1 kiloparsec, while the HST resolution is much better, 70 parsec. This is one example. It's the same galaxy as before. Sorry, this is the same galaxy as before, but now this is the HST, multi-wavelength image. And so, yeah, this is an example of another jellyfish galaxy that we study, but GASP is much more than just jellyfishes, and I just want to stress this in a couple of minutes. So, 3 topics we address, and let's say these are the main questions that we asked. And here, if you want, whenever you like, I pointed you to the relevant papers. We studied star formation in many different ways. Star formation in the disk of the galaxy, star formation rate-mass relation, integrated and spatially resolved, at different redshift. We studied star formation in the tails, in the strip tails. We will hear about that from someone from GASP. So the clump properties, all the clump properties, and of course the quenching, the subsequent quenching and the post-Arbus population. Different star formation rate indicators were used, and simulations that are also an important part of GASP showed the lack of effects of stellar feedback on the run pressure stripping rate. There are many unexpected results from GASP. I just mentioned one. Another one that was unexpected was the relation between AGN and run pressure stripping. So a number of works on AGN feedback, run pressure stripping, and AGN activity. GAS, of course, is the main focus, as is the main focus of this meeting, and fundamentals to study the different phases. So we have a number of H1 results, molecular gas results, radio continuum tails and direct magnetic field detection, X-ray tails, ionized gas from MUSE, of course, including the diffuse ionized gas, from which you can study gas metallicity, and we found also evidence for mixing of stripped interstellar medium with the hot intercluster medium, which is important, relevant for a number of works, for example, CGM works. Also here, simulations, of course, simulations of run pressure stripping of both halo gas and disk gas. And of course, a number of single galaxy detailed studies of the gas and stellar components, including stellar kinematics and so on. Okay, last one is, of course, environment. As I said, lots of results on clusters. For example, how important is run pressure stripping in galaxy clusters at low redshift and at intermediate redshift. The orbits and the phase space of run pressure stripped galaxies, the direction of the tails, the cluster dynamic, the importance of cluster dynamical status, and outside of clusters, there are many works here from Benedetta. We really saw many different processes, even in the same group of galaxies at the same time, and specific properties, processes in galaxy filaments, and case studies of gas accretion emerging. One thing that is probably not the focus of this meeting, but that I think it's an important result from GASP, is the impact of the round pressure stripping on the galaxy structure. Because even if round pressure is only a gas effect, there are indirect effects on the galaxy structure. Unwinding of spiral arms, spectromorphological evolution from spirals to S0s, bars, and so on and so forth. Okay, now that you've seen all the 70 GASP papers in once, you will not see much of that anymore, except in a few cases. Now we go to the practical things. Okay, here you need to pay attention. Okay. If you need a participation certificate, it's already ready with your name. You can download it from this drive here. The Wi-Fi to connect to is Ospiti, and the password is GASPISA capital 2024. The coffee breaks will be here in the garden. The lunches, which are included, so don't walk away for lunch. We have wonderful lunches upstairs. You just follow me or somebody from the lock to go upstairs. The only lunch that is not included is Wednesday. Okay, I'll tell you why. Toilets are there, at the back, to the right, to the right. Of course, we would like to have your presentation, please, by the end of the conference, uploaded at this link and this QR code. We hope that laptops will only be used for presentation, but if you need to charge your laptops, you can do it here at the desk or at the secretary desk. Okay, don't go in the back, because there is our technician that has to take care of many things. As you saw at the beginning, you were given a paper for, let's say, giving the permission to post your recorded talk online. If you agree with that, if you agreed with that, we have your signature, because all talks are recorded, okay, and they will go online. If you don't want it to be put online, then you just don't sign the paper. There is a Slack channel, some of you already entered, where I will post also this presentation, and where there are some information, some tips for restaurants I put there, and some things like that. Okay. Okay, now for the fun part. The badge you have gives you free entrance to the Museum of the Opera Primaziale Pisana, which is where we will go through the museum to go for lunch, which is really nice to see. And you can go anytime. It should also, I saw a man at the end, it will give me confirmation, I'll tell you later, it should also give you entrance with the badge without an additional ticket to the cathedral, the Duomo, as we call it here, and the Camposanto Monumentale. Okay, so just to be clear, we are here now. Lunch will be served here. This is the cathedral, you can't miss it. This is the Camposanto Monumentale, which you enter from here. The Battistero is currently closed for restoration, so unfortunately we couldn't give you that ticket too. Okay. So Wednesday there is the free afternoon. We will finish quite early at 12:30, and there will be no lunch provided. For those who registered for visiting the tower, it's €20. This we couldn't offer really, because there will be 3 groups going up, going up the tower at 6:45, 7 o'clock, and 7:15. If somebody wants to come and didn't sign before, there is still a possibility to do it today. You need to be in front of the tower 10 minutes before your turn. We will give you the tickets for this tomorrow, which you must not lose, because if you lose the tickets, we can't do anything. So tickets will be distributed tomorrow, and the ticket will have the time of your ascent to the tower. Important to know that the only things you can take with you on the tower are phones and cameras and video camera and stuff like that. You cannot bring bags or backpacks of any kind. So there is a garderobe which you can use with your tower ticket before the appointment. You can go, or I'll show you where. You can go here. There is an office. You can go there, and you can leave your bags, and you can pick them up later. Okay? Okay. Also, I would recommend a tour of the medieval walls. They give you really a different perspective of the square. This is where you go up. This is not included with the badge because it's a different organization. It's not the OPA. So you can go up here, and you can walk this side up to here, and most importantly, you can walk this side for 4 kilometers all around town if you feel like up to it. Okay. Group photo is tomorrow afternoon, and it's at the end of the afternoon session. That's because really all the things that I'm telling you are best done at the end of the day, after 6 o'clock. And I don't tell this only because I want you here for the, for the conference. It is true because the light becomes much better. So best light to do all the things I suggest is between 7, 6:30 and 8, 9. Sunset is 10 to 9. So tomorrow group photo at the end of the afternoon session. Don't walk away. We all go here on this part of the grass. Somebody will go up the walls up here and take a picture of us, all of us, and all the square. Okay, so. Don't miss. By the way, most people don't know it, but you can walk on the grass everywhere except this part. This part is currently closed. Is closed, this part. Everywhere else, where it's not written, do not walk on the grass, it means it's allowed. So we can walk here. Okay. On Thursday we have the dinner, the social dinner. And before that, since we are close, we go to visit the charter house of Calci. It's a really beautiful place. Calci is a small village. It's only 11 kilometers from here in the Val Graziosa. It's called the Pretty Valley. So again, as soon as the afternoon session ends, there will be 2 buses waiting for us in Via Cardinale Maffi. It's very easy. I will tell you again, but you just walk out left, and right. It's like 50 meters from here. And the buses leave at 5:15 p.m. sharp. So there will be no time to go back to the hotels, leave the stuff. So if you can, please do not bring your laptop on Thursday, if you're not a speaker. And if you are a speaker, you can give them to me. I put them in my car, and then I come with the car to Calci. So we will have a short visit of the charter house and then the social dinner. And we will be back at Via Cardinal Maffi before 11 p.m. Okay. Dress casual, walking shoes. It's a rustic restaurant. It's not an elegant one, but it's nice. Okay, this is to embarrass Sirio even more. Thank you. Well, okay. Friday evening, this is just for information, this will be in Italian because it's a public conference for the citizens of Pisa, and will be in Italian. It will be on Friday, 8:45 at the Gipsoteca of the Università di Pisa. I tell you this because even if you will not be at the conference, clearly, I advise you, we will open the gate, let's say 8 o'clock, 8:15. If you want to come by, enter and see the Gipsoteca. The Gipsoteca is a place where they keep all the statues, reproduction from many famous statues from all over the world. It's an occasion to enter free. Normally you pay the entrance, but if you want, you can come by, see the Gipsoteca, and then go out. But of course, the people from Pisa will come for Sirio to hear his conference. Okay, last thing in the last 5 minutes. Just to tell you this, the Pisa is much more than, this is called the Miracle Square, the Piazza dei Miracoli, the Miracle Square where we are. There is much more to see, which again, I advise you to see at the end of the day, not during the day. But of course, Wednesday afternoon, before we will climb the tower, it will be a good occasion. Three things, I mean, you all received the map and the leaflet from the tourist office. In the map, there is everything you can possibly think of, but, you know, even too much. The three things I would strongly suggest are, of course, Piazza dei Cavalieri, this one is unmissable, okay. Botanic Garden, if you like, is just around the corner here, one street to the left. It's the first university botanic garden in the world. And then all the Lungarni. Lungarni means essentially all the streets around the river Arno, all around you. Yes. And along the Lungarni, there are a number of beautiful things to see, lots of things which you can enjoy. Churches like Santa Maria della Spina, San Paolo a Ripadarno, San Silvestro. There are really a lot of things. There is some fortresses, Cittadella, Giardino Scotto. I put a list there. And there are 4 musea here, which one can see, which are very nice. 2 national ones at Palazzo Reale and San Matteo, Museo di San Matteo. Here there is a museum of old ancient Roman ships, which is also well done. And here, not on this map, but it is on your map, there is Palazzo Blu. You can't miss it. It's a blue palace. It's really. And they have a temporary and a permanent exhibition, which is also quite nice. Okay, I'll leave you with this, but in the slides, I just put a couple of extra things. If you are lucky, you stay in the weekends. There are 2 things really close to Pisa, which are, I would strongly suggest. One is Parco di San Rossore. It's a regional park, a natural park, very big, with pine trees, wildlife, lots of trails. It's only 6 kilometers from here, but unfortunately there is no public transportation and stuff. And free entrance. Inside you can walk, hike, you can go with the horse carriage. It's really nice because they bring you also to some stuff where you're normally not allowed, but you need to reserve. It starts at 2:30 p.m. every day. You can book. You can rent bicycle, rickshaw, electric train. You can go electric train, but only Saturdays and Sundays. So in this case, I don't have to tell you that. They make it really difficult to get any information. Even, you know, there is no English website, there is nothing. But if you want to know about this, I have a leaflet that I personally had to go to pick up at Parco San Rossore. Anyway, for the weekend again, I hope the weather will stay like this. Of course, there is the sea. The sea is like 13 kilometers away, the sea and the sunset in the Mediterranean. There are 2 places, Marina di Pisa. This is Marina di Pisa, which was devastated by the sea storm a few months ago. And you still see the scars of it. This is destroyed essentially in this, but it's still beautiful. While there is also Tirrenia, which is sandy, big beaches. And it's a very nice walk all the way from Marina to Tirrenia. And this one has public transportation, very easy. Regular buses, number 10, from town every half an hour. It takes 25 minutes, and it's easy, or you can bicycle. Okay, I think I've said it all, and I wish you all a really, really nice meeting. Let's enjoy scientifically and generally socially. So thank you for coming, and enjoy. Yes, here we go. And this. And this, avevo letto, quando è finito lui, li riattacchi per il prossimo. Okay.
No, it is not automatically coming up. Oh, there it goes. Take this time. I'm Benedetta Vulcani. I'll be the chair of today's session. So let's start. It's a great pleasure to have Rob Kennicutt. They will talk about drivers of star formation in galaxies, observational clues from the local universe.
Yeah. Thank you. Thank you very much. For those of you wondering about the affiliations, I retired from Cambridge, amazingly, 7 years ago. Hard to believe. I really did retire. I reached retirement age, but only lasted a year. Now I have 2 jobs. Go figure. The Americans never let you retire, basically. So I'm supposed to introduce the second of the themes that Bianca presented, drivers of star formation in galaxies. This is a field that's just progressed enormously over my career and even faster now. The bookmarks here are, I just thought I'd show you the first paper I know of that used the term star formation rate. It's the famous Schmidt law, a paper in 1959 where he derived the first analytical models of galaxy evolution, amazingly. And then Beatrice Tinsley's thesis paper about a decade later, the first numerical models of galaxy evolution. That's how we started, and here is where we are now. Amazing, right? Tremendous pace of discovery. Webb results, this is from Feast. Maddow diagrams that are now pushing, right? The teams in redshift and numerical simulations of remarkable fidelity. So how can I help you in the first 25 minutes? There's no way I can compete with most of you who are producing these wonderful results from Webb and ALMA and simulations day by day, every day on the archive. But what I can offer that most of you may not have is perspective. Somebody who's worked on the subject for about 40 years and seen how the field has progressed and how some problems remain to this day. So I'm going to try to give you very top level. As Bianca said, people from many communities. I'm going to present results that many of you know since grade school, virtually, but in other subjects where hopefully for everyone something a little bit new. So the way I'll do it is I'm going to talk just examples of areas where we've made enormous progress, especially in the last 10 to 20 years. Those are in green. I won't cover all of them, and you don't have to read every one of these. I'll go through many of them. And then in red, the challenges which remain for all of us to solve maybe over the next 20 years. So many familiar XCO, right, alpha, that's one of my things that drives me nuts. IMF, of course, magnetic fields always has to be on the list. I'm going to begin with this one down here. If there's sort of an overarching question that's dominated the subject now for many, many years, it's the big debate. Is star formation driven from the bottom up, from molecular clouds on up, or top down? Examples, those of you alveo people like me have been around. If you've ever met Nick Scoville or Leo Blitz, they will say, who needs H1? And they still do this at meetings, right? It's all, if you measure a molecular mass, you've determined everything. And then when I was at Cambridge, Jerry Ostreicher, that's Eve's father, and the Plumian professor before me, would torment me by saying, these Schmidt laws mean nothing, these molecular clouds. It's all, the rate of star formation is just the rate of cosmic accretion, cold accretion from the cosmic web. You measure that, you measure the star formation rate. The rest is just icing on the cake, describes morphology and things like that. So obviously crazy asymptotic positions. So anyway, you notice I have this in green. So what's the answer to the question, bottom up or top down? And either both or neither, I would say, right? This is one of the big paradigm shifts. We now think, in fact, it's a multi-scale process, multi-processes on all scales, neither top-down or bottom-up. These processes all interact with each other, and you're not going to understand star formation until you understand all of them. So here are a couple of examples of this ecosystem. This is a quote from Martin Rees after I complained to him about Ostreicher. He really meant, is star formation like climate? Is it a big ecosystem? And, you know, I think like everything else Martin talks about, probably right. If you didn't like those examples, here are many, many more. Or, bathtub, the large-scale version, of course, the bathtub model, I put that on as well. But, this is more than hand-waving now. Let me try to get this simulation going. I realize I need my reading glasses to see the cursor here on my laptop. Here's a simulation from Andrei Kravtsov's group. This was hand-waving for many, many, many years, but really numerical simulations have really turned this into a quantitative model that does really seem to work. And I guess I probably have to stop it to be able to, there we go. There are very important implications for this meeting and for the whole subject of star formation. It tells us that star formation fundamentally truly is multi-scale, and by multi-scale I mean a dynamic range of at least 10 to the 10 from essentially the 1 AU, which is the diameter of a red supergiant before it explodes, out to the accretion radius, the virial radius of a galaxy. By the way, the climate ecosystem is the same dynamic range from the size of a raindrop to the diameter of the Earth, basically. And this has been reflected in the way we attack the problem, particularly observationally. When we began studying, beginning of my career, you would try to study galaxies at one wavelength, H-alpha, infrared, ultraviolet. Nowadays, the typical surveys are multi-wavelength, and they focus much less on the behavior of galaxies or star formation in any one component to these connections, these interconnections between different phases, different scales, and so on. And finally, final reminder, the path to understanding star formation passes through subjects that won't be represented probably at this meeting. This is actually, in fact, a meeting on stellar evolution. If you work on redshift, I attended a preliminary exam. I was on the committee for a student last week who works on redshift 10 galaxies with JWST. Confessed he never attends colloquia very much unless they are on JWST at high redshift, and his committee members gave him a rather stern rebuke saying, if there's a talk on supernovae or numerical simulations, binary evolution of massive stars, you'd better attend those, or in 10 years you are going to be left behind. Enough preaching. So there is one breakthrough. I'm not going to cover all of them, obviously. Another one, I think, is our ability to measure star formation rates in galaxies. We really can only do this accurately, meaning factor of 2 accuracy, in the 1980s. Now it's routine to apply Prospector or Segal to observations of redshifts as high as you like and get tens of percent accuracy star formation rates. It began, of course, with individual wavelength observations, then combinations of dust-obscured and dust-emitting tracers. Just one example, the precision to comparison of different methods. And nowadays, of course, if you get enough wavelength coverage, you can do full SED fitting. This has advanced the precision immensely, although be careful, these programs produce wonderful corner plots and Bayesian MCMC fits that give you the false security that those systematic errors don't exist. And in fact, many of them are really just weighted averages of these 2 wavelength recipes. And because they try to measure more than star formation rates, they try to do star formation histories, extinction, et cetera, you often can run into degeneracies, especially when the models were calibrated, say, on present-day galaxies with 10 billion-year-old populations, and you apply them at, say, redshift 10, there are going to be problems. But obviously, enormous progress. Also, the 0 points of these scales, much more reliable. You can either do this with resolved color magnitude diagrams in populations outside of their birth clouds or by looking at YSO statistics within the clouds. You see, I'm going to go through things very quickly. Number 3, I've talked about multi-scale, so I'm going to really focus on really small scales for part of this. there's another long-standing question is if you go to small enough scales at or within molecular clouds, do you reach a unit where essentially everything becomes linear? The number of the massive stars forms essentially scales linearly with the amount of material you have. And the answer, I think, is a lot of progress, although the experts still disagree on that. Here's an example. In the early part of this century, we finally either nowadays with ALMA, but even before that through extinction mapping of molecular clouds in the Milky Way, you could identify individual protostellar cores. These are the things that are going to become individual stars or individual multiple systems, not clusters, smaller than that. And a very still controversial result, starting with Alves's work, that the mass function, the cloud mass function, CMF, seems to mimic the Krupa or the Chabrier initial mass function with obviously an offset to measure, accounting for the star formation efficiency. I gave this talk a month ago, not this talk, but this plot a month ago at a meeting that was full of experts in this subject, and they castigated me afterwards. I had a side saying this is pretty much an accepted result. It's still being debated, but there's a wonderful review of the IMF coming out this fall you can find on the archive by Hennebel and Grudic if you want to read all about it. Now, that result applies to individual stars, but we all know that most stars, and probably all massive stars, form in clusters, aggregates, more massive aggregates. And so that is a different process. It is, but there seems to be a fundamental unit associated with those so-called molecular clumps, typically several hundred to thousands of solar masses within the cloud. I'm going to skip ahead a slide and come back. Part of this paradigm change was the realization with Herschel and ALMA that molecular clouds are nothing like the spherical cow, virialized, uniform density clouds that were dreamt of, back when they were discovered back in the 1970s, but in fact are very fractal, filamentary structures, lots of substructure. Here's what they mean by filaments. This in dust mapping with Herschel. Here you are, torus with ALMA, and it's in these filaments, right, where you see the young star YSOs forming. And if you ask Thomas Henning, he will say at the intersections of these filaments is where you see the really massive clusters and the massive stars. Should be familiar to you. This is just like the cosmic web, right? Galaxies forming in filaments, clusters and intersections of filaments. It'd be interesting to see if that holds up, but it's very intriguing conjecture. Coming out of this, an important result is that people always ask, what is the efficiency of star formation in molecular clouds? In molecular gas, it depends even on scale within clouds, right? In these cores, protostellar cores, close to half, plus or minus, of order 10%. Even those clumps host the star formation, most of the mass doesn't go into stars. And then in all that diffuse stuff in between, very little, almost none at all. So star formation efficiency is a much more complicated beast than we might have thought. A result, maybe even more controversial than the others I've mentioned, Heiderman and Evans et al. Lada, back in about 15 years ago, argued that essentially presented what I've just described and argued, in fact, there's a threshold surface density within the filaments above which you see essentially all the star formation, still debated in the subject, but certainly some truth to it. How universal it is, though, really to be debated. So that's that one. Got a couple more to go. This enormous advancement in our understanding of the connection between molecular gas and star formation now extends to galaxies as well, as many of you know, because you're going to present many results here. ALMA now is the enabler to look at individual GMCs in external galaxies, covering a very wide range of physical conditions. And Webb allows you to trace the dust emission, in some cases the star formation, directly on comparable subarc second scales, so you can really drill into this connection now on scales from tens of parsecs up to kiloparsec and larger. And of course, there's a whole alphabet soup of very important projects. I've just listed a few here, and I'll show you a couple of results. I've just picked FANG, 2 results from FANGs for examples. We're going to hear many, many results from Almaquist, FANGs, Feast, etc. as the time goes on. One result seen in all the surveys, going back to early surveys by Leroy and others, Beguil, is a very linear, this linear connection that the star formation is roughly proportional to the amount of molecular gas, extends all the way up to the integrated scales. So whenever you have a linear relation, doesn't matter if it's per unit area, per unit volume, you preserve that linearity. Starbursts tend to sit up here, we'll get back to that. The other interesting is another long question. What is the lifetime of molecular clouds in galaxies? You had to be there in the 80s and 90s to know the ferocity of the debate. Debate is too mild a word. Fights over this. People arguing everything from a couple of million years to 200 million years. We now probably have answers thanks to the combination of ALMA with various multi-wavelength star formation tracers. This is from Melanie Chavance, and it shows distributions of lifetimes in several FANGs galaxies. Interestingly, the purple is the period from which star formation, onset of star formation, you see those lifetimes or destruction time scales are pretty quick, a few million years, makes sense. Massive stars, feedback is really doing that. But in fact, they spend the majority of their lifetime before building up, basically, to the triggering of the main star formation. And if you take that total time scale, 20, 30 million years. This time scale, the time to use it up in a disk, is 2 billion years, almost everywhere in normal disks. Divide this number by this number, you get 20 to 100. In other words, there's essentially enough time. Molecular gas will sustain star formation for tens of cycles before it runs out, but much less than the Hubble time. We'll come back to that. Okay. This is the last, I think, of the things where we've made advances. I have to have it, right? Scaling laws. You're familiar with the Schmidt law, I'm sure, almost all of you, but there are many more. Remember the famous star formation rate stellar mass relation is another example of a scaling law. And I've just put up 3 others. There are many. I won't even take time to name them. These are not independent correlations. Many of them are projections of more fundamental correlations that we're still trying to figure out. This is illustrated very nicely in a plot I hope we see soon by Lynn. And there we go. Here she goes. This is a 3-dimensional projection of the star formation. The Schmidt law is one of them. Surface density, star formation density is another. Molecular gas, scaling laws, and so on. And and these are important for, I think, the reasons you know. It means we're not dealing with random processes. They're physical laws driving these, and that's one of the holy grails we try to attack. Okay, I spent a little more than more time on the successes. Well, let's look at the challenge. Challenge is the new word. It used to be problems, but politically correct to say challenges ahead. What are some of the problems that just defy answers up to now? One at the top of my list, frustration for me over my career, is when can I trust a molecular mass of a galaxy, especially one at low metallicity or low mass or very high star formation rate? The famous alpha CO, XCO problem. It's particularly acute in the highest star formation rates, where there have been claims now for 15 years of a bimodal star formation law, but how bimodal depends so much on what you assume for converting CO intensity to star formation rate. It's being worked on. Come to the next slide. Thank you. I'll be quick now. One way to address this is use dust as a proxy. Assume that the dust is well mixed with the gas. Choose galaxies where the dust to gas ratio doesn't vary by much. And what you find, this is work from Karen Sandstrom and her students, Chang in this case, showing significant, these are variations in alpha CO across disks of galaxies. And the consequence, if you adopt that, is to produce some nonlinearity in this, this universal depletion time relationship that we have seen earlier. A related problem for which this has an important role is star formation have multiple modes? Now, different communities interpret this question differently. In the galactic community, that means is low mass star formation a different mode from high mass? Is clustered star formation have a different mode? For extragalactic studies, it's often, are there multiple modes in the star formation laws themselves? We know of one for sure. At low density, there's an abrupt drop in the star formation efficiency at about the point where the primary cold gas phase goes from molecular to atomic. But the ongoing debate is at high density, the starbursts we know have much higher star formation efficiencies. That's almost by definition. They're chosen to have these high efficiencies. And is that a separate mode or not? The answer has been stymied by not knowing what to do with XCO. But here, this is the one new result from my group. Chengpeng Zhang and I have been using data from the literature to essentially use dust again as a proxy for the star formation, Dustpedia and large samples. This is the result Mia de los Reyes and I published a few years ago. The new results show, yes, there's a turnover toward a linear relation in the starburst galaxies, but in fact, the gap in between is filled nicely by infrared luminous galaxies that aren't circumnuclear and by the central regions of these galaxies. So maybe the answer is yes, there's sort of a mode down here, threshold, a turnover here, but it's not probably nearly as abrupt as we saw before. Got a couple of minutes left. To me, the real challenge, the biggest challenge ahead is this one. How do you get from the H1 and form the molecular clouds? This breakthrough of knowing that molecular gas correlates very, very tightly with star formation is a wonderful victory, but most of the gas in galaxies is atomic, not molecular, and so the question really becomes, what regulates the formation rate of molecular gas? That's a much more challenging problem. Unlike the molecular gas, which seems to have this near universal depletion time in disks and is only a factor of few higher in starbursts, if you look at the ratio of atomic to molecular gas across the Hubble sequence or across the mass sequence, there are 3 orders of magnitude and 1,000-fold change between them. And thresholds probably have something to do with that. So we understand very little of that. We're needing SKA and GVLA, the next generation of radio telescopes, to probably help us crack that problem. But I think maybe the biggest unsolved problem is that one. And then finally, I know I'm out of time. That's okay. Feedback, thank you. 1 minute's perfect. Feedback is a key, of course, to understanding all of that. We'll hear many talks. It deserves a review of its own, and I think it's getting a review of its own or two here. There are very interesting scaling laws that aren't understood. How is it that the velocity dispersion of the ISM correlates with the star formation with a Faber-Jackson-like relation? I'll just end with an editorial. This is my next to the last slide. Again, sorry, break out the stupid reading glasses to find the arrow. Maybe I just have to click. These are Tigris simulations of a segment of discs by Kim and Ostreicher, just as eye candy, an example for you. Nowadays, if you work on cosmological star formation on large scales in galaxies, you couldn't imagine understanding the problem without numerical simulation. TNG 50, Eagle, Fire simulations. They have become not only useful but indispensable. However, it is my impression for people working my subject that people read these papers, they say, yeah, nice, but they have not inhabited the core of our thinking yet. And I think these simulations are reaching this state of maturity. They have a lot to teach us. And so I think, message to you all, pay more attention to this. I am at the end, just to say we're not done with the challenges. There is a fuller list of them. I won't take them through you, just to assure you, yes, lots of progress being made. I hope some of you learned a bit from that, and lots of work to be done in the future. Thank you for your patience. Well, if you're going to talk, you need a mic.
So I have one comment and one question. So we are still discussing about the lifetime of molecular clouds, just to remind you.
Yeah.
The reason is because the current analysis is a population study, cloud with star formation and without star formation. And from the fractions, they convert that to lifetime. But there's an underlying assumption, which is, after one star formation cycle, cloud dies, but cloud could just continuously, keep forming stars with 20, 30 million years as the duty cycle, but the lifetime could be longer. So that's the other argument. So that's a comment. And then the question is about the index of Kennicutt-Schmidt relation. And I'm always very interested in if it's linear or non-linear, because it has very different physical meanings. And I just want to understand what you said correctly. So are you saying that that problem, the index problem, we have to solve XCO and definition of the star formation rate? Is that what you're saying? So unless we solve those questions, we cannot answer the question of the index of the Kennicutt-Schmidt.
Yeah, the current, if you assume a constant XCO everywhere, which is actually more consistent with the dust data than any other, you get the 1.5 roughly relationship that basic physics predicts for the normal disks. But in the starbursts, which are totally molecular dominated, the slope becomes linear there. If there's one value of X for starbursts and one for normal, of course slopes won't change for those subpopulations, but there are models, for example by Bellato et al., which argue that X is a continuous function of surface density, in which case, obviously, that would affect the index. Yeah.
Thank you very much. Very instructive for me. I will have a question related to simulations, because I have the feeling, I'm an observer like you, so how difficult it is to really to put the simulations in the context of observables, because I have the feeling they're not able to trace down what we observe indeed. So do you have a recipes for them? Thanks.
The trouble, yeah, it's an excellent question. And the trouble was, until maybe 5 years ago, the recipes they used for the simulate were Schmidt laws. So, and I ran into this problem when this bimodality I went to the simulators and said, in your simulations, do you see bimodal? They said, well, we take whatever you give us. So the simulation will produce what, you put in. Nowadays, the more modern ones, there are other prescriptions, use free fall times, more genes, prescriptions. They tend to produce scaling laws if you do them on the back of an envelope. So in some sense, there is more decoupling, but I would say, no, I think uncertainty in the subgrid, both for the star formation, relation between gas, say density, star formation rate, and the feedback for sure, which subgrid is almost necessary, are still limiting factors. But the smaller you can go in scale, the more you can begin to do something ab initio. But at the cosmological simulation level, where you're dealing with huge particle size, no choice but to use subgrid empirical descriptions, I would say. Somebody can correct me if I've gotten that wrong.
May I ask, in the recent work of your group, you used M dust instead of M gas. Will that introduce extra complexity due to the metallicity dependence of M gas M dust ratio?
Yeah, are you asking about variations in dust to gas ratio?
Because I noticed your group that use M dust instead of M gas.
Yeah, exactly. Yeah, that is, you substitute one set of systematic errors for others when you go to dust. Instead of variable CO to H2 conversion, if you're using dust, you have to rest on an assumption of a constant dust to gas ratio. We don't ever plot, we always just plot things as a function of dust mass. So, we choose galaxies of a sufficiently high mass that they tend to be in the regime where X does not vary much, but yes, it will bias the slope if there is a systematic change in dust to gas ratio. And you go to papers like Roumet, Rouillet, and so on to try to explore the error bars that which we do. So yes, it's qualitatively important, but it won't change these results in any major way, I don't think, because we're careful to throw out the galaxies where that assumption would be questionable. Okay, thank you.
Thank you. I think we need to move on. Thank you. And the next speaker? So the next speaker is Fariña, measuring past gas accretion in local universe galaxies.
Okay.
It just takes time.
Okay. Well, I'm just going to introduce myself. Oh, there we go. Hello, everyone. My name is Fariña, and I want to talk to you about this method that we have developed that allows us to measure the gas accretion history in local universe galaxies. So to this audience, I really don't need to spend a lot of time explaining how important cosmic gas accretion is. It's just a reminder that galaxies accrete gas from the cosmic web, which is what allows them to sustain their star formation over time. And it's also important for what I'm going to tell that this gas has low abundance. This low abundance means that the ISM is diluted when the accretion happens. The main problem that we have with this, at least I think, is that it is very difficult to measure the gas accretion. The filaments as they come into the galaxy tend to be very optically thin, and there is an offset between when the accretion happens and when the star formation increase happens, so it's hard to couple them. In order to solve this, we are applying full spectral fitting technique to obtain the star formation histories and the chemical enrichment histories of the galaxies. For those who are not too familiar with this technique, the main idea is the stellar spectra of a galaxy is the combination of all of the stars that compose it. The stars were formed in successive bursts of star formation. So if we take spectra, templates of the spectra that a population of a known age and metallicity has, we can fit the observed spectra with them, and this gives us the weights of the different populations that compose the galaxy. We can convert these weights into star formation history and the chemical enrichment history because we know when the stellar mass was formed and the abundance that the stars had, which we presume is the abundance of the ISM when they were born. So in a closed box model, the star formation history univocally determines the chemical enrichment history because you have a cloud of gas, the stars forming it, deplete it a little bit, and then progressively inject metals in a known way, because you have this many stars, you're going to have this many O stars, this many lower mass stars that are going to inject known quantities of metals. But this is not the truth. In truth, the box is leaky at least, and there's interactions with the gas, such as inflows. So what we do is we apply this very simplified model above, which is we take an initial cloud. On this, the star formation history acts, enriching the medium, and then inflows, we are sort of bypassing outflows. Inflows will dilute the gas to produce the chemical enrichment history. So we have the star formation histories, we have the chemical enrichment histories, and we can make reasonable assumptions for the initial conditions. As such, we can isolate the variable of how much gas is accreted. At the bottom right, I give you a sort of an example. On the bottom, there's a star formation history, and on top, I show you the solid line is the observed chemical enrichment history, but the dashed line is the chemical enrichment history that this star formation history will produce in a closed box without dilution. You can see that we observe significantly lower metallicity. Something is diluting the ISM, and we can take this difference to estimate how much gas is being accreted at each time. This is a schematic of how it works. We take the manga sample, we make a few refinements, we exclude currently active AGN as well as highly nuclear galaxies. We end up with about 8,600 galaxies. We apply Piper 3D, which is a full spectral filtering code, to these spectra to obtain the star formation histories and chemical enrichment histories. Then we make reasonable assumptions on the metallicity of the gas that is being accreted. The initial metallicity of the gas, we take it as the oldest metallicity that will resolve in the galaxies, and then we estimate the amount of gas that galaxies start with, which we use measurements of the gas fraction at high redshift. We plug this into a galaxy chemical evolution code. We use the one from Rocafabrega 2021, and this is crucially a time-resolved injection code. So no instant recycling. We form populations of stars, and then the stars inject the metals at the time that they do, depending on how resolved your time is, but they inject it at the correct time. And then the code compares this star formation history with the gas that we have now, should produce this metallicity. But we measure a different one. How much gas do I need to accrete right now to match the metallicity? And this gives us the gas accretion history. Naturally, especially for those who are familiar with full spectral fitting, we have several caveats and problems. This is a technique that is known to have a lot of degeneracies and systematic errors. Also, the older populations have lower light fractions, which makes it that they are harder to resolve. And this is our initial conditions, which means the errors propagate forward. Another important problem is that we are assuming that all dilution of the gas is from only gas accretion, and there are no outflows. I will touch more on this later, but for now, we assume this works. So certainly you have to be very careful of how you interpret the results, but I think they turn out pretty well. Here are finally our gas accretion histories. On here, I'm showing you the gas accretion histories that arise from the histories of galaxies. We average the star formation on the chemical enrichment histories first to get them more reliable. Within mass bins, stellar mass bins, current mass, and we see that the more massive galaxies have higher accretion rate generally at all times, but also they have declined much more, they have a much steeper decline towards recent times. We are here right now, to the left. The less massive galaxies have a lower but steadier gas accretion history. On the right, I'll show you the exact same curves, but we scale them with the current stellar mass. You see that they all bunch up, they become much closer, showing that the gas accretion rate is sort of proportional to the halo mass, more or less. It's sort of a proxy. Here on the bottom, we make some actual quantitative comparisons with the classic simulations of Keres and van der Voort, and they reproduce a Milky Way-like galaxy. So we chose this bin, which is the mass that is more or less as the Milky Way, and they predict a peak accretion of 10 to 30 solar masses per year. We find 4.8, factor of 2, already not too bad considering what we're doing. But the current rate that they predict is about between 1 and 3, and we have 1.2, so we actually match, which is fantastic news. One of the great advantages of using full spectral fitting is that we measure galaxies locally. We don't need to go to high redshift to get the histories or to get how things were in the past. This allows us to get very rich samples with lots of galaxies and with well-determined parameters such as the morphology. Here we see that at the same mass, same stellar mass, later type galaxies have a more sustained gas accretion. But my favorite is the one on the right, where I'm separating the galaxies based on their current star formation status. Are they star forming, are they green valley, or are they retired? Now, the history, back here, they're all star forming. We're separating their histories based on how they are today. And we see that the currently retired galaxies have a very quick, very early decline in their accretion rate, which is what explains why they are not forming stars now. But look at the star forming and the green valley galaxies. Their recent history is almost identical. These are different galaxies that we're averaging. Until 500 to 1 year ago, when green valley galaxies dropped their accretion rate to the same rate as the currently retired ones, but the star forming ones still maintain a decent amount of gas accretion. This is very important because, as we can see, currently green valley galaxies used to be star forming galaxies not too long ago, which fits, but also their current accretion rate is the same as retired galaxies, but not their current star formation rate. These galaxies would be in between. This is telling us that first they run out of gas, first they lose access to gas accretion, and then they start to quench, which means that it is the consequence of losing access to gas accretion that means the galaxies quench on average, at least. Because we have the amount of gas that is accreted each time, we have the amount of gas present at each time, which allows us to measure the star formation efficiency history. This is where the lack of outflow is going to be more important. And I don't have time to explain all of these plots, just focus on this one here, which is the star formation efficiency history with, divided by mass bins. And what you see is that for recent times, we have what we know. Ooh, okay, let's go fast. The less massive galaxies are more efficient than more massive galaxies. But if you go back, the opposite is observed. There's an inversion. More massive galaxies used to be more efficient than less massive galaxies. This is something that has actually been predicted and demanded by certain models, but as far as I know, this is the first time that it's actually observed, sort of observed. And everything has worked out well for our averaged histories. That is, we average first the star formation histories and chemical treatment histories before plugging them into the model so they're more robust. If it works, let's go to individual histories. Because it's 8,600 histories, we can't just show them. So on the left, I'm showing you the total amount of gas mass that is accreted by a galaxy versus the total amount of stellar mass that is formed during the time that we resolve. This is the one-to-one line, and we see that galaxies are tightly hugging this one-to-one line, but they are above, meaning you cannot form more stellar mass than you accrete gas. They have a very tight correlation, and we also see that the currently star-forming galaxies, which are the ones that are greener, are above. So they accrete more gas for the amount of stars that they form. And here on the right, I'm showing you that the tau 80. The tau 80 is a parameter that tells you the shape of the gas accretion history. So if it's the amount of time that it takes to accrete 80% of the total gas mass that is going to accrete. So if it's low, it means we have accretion bias to the past. You have a high peak and then declines. If it's high, it means that this accretion is biased towards the present. It's a sustained or with a recent peak of accretion. And again, the color is the current star formation rate. This is from emission lines, no bias with our sample. And we see a clear segregation such that the more the galaxies that are star forming today are the galaxies that have sustained or recent accretion of gas, whereas the galaxies that have declined are below, are not star forming. So the entirety of the shape of the gas accretion history can determine us whether a galaxy today is star forming or not. And I also have not a lot of time to explain this. This is the same with the star formation efficiency. And look at this plot here. This is the slope of the efficiency history, and we see that the star-forming galaxies are very tightly located around 0, which means flat star formation efficiency history, whereas the retired galaxies are below, have negative slope. And I promised, in history of time, that I would tell you about the outflows and what's happening here. How bad is it that we don't take them into account? So the best way to check this is because outflows, what they're going to do, they're going to remove gas. So we take our predicted amount of currently remaining gas, which is the amount of gas that is initially plus the amount of gas that is accreted minus the amount of gas that is removed by forming stars. And we compare them to the H1 manga survey, which measures actually the current amount of gas that is in the galaxies. This is the one-to-one line, and we see that we are shifted to the right, which is good, because this means we are over-predicting gas, which is exactly what we should be doing if we are not taking into account the mechanisms that remove gas. So, so far so good. If we take the difference between these two for each galaxy, this is the amount of gas that presumably has been removed. Divide this by the total amount of stars that have been formed, and this is the average mass loading factor. What we get is that on average the mass loading factor is 0.96, about 1. This is lower than the typical value, which is 2.5. But you need to take into account this. The typical 2.5 value is instant. It's the amount of gas that is currently going up out of the galaxy divided by the current star formation rate. Ours is the effective. Some of that gas that goes up is going to come back down, and we only look at the result at the end. So in order for us to have a perfect match, all we need is that 60% of the gas that goes up in an outflow eventually comes down back into the galaxy. And my theoretical friends tell me that 60% recycling rate is good. It's a reasonable value in line with what they expect. Don't know if I have a lot of time to explain this. We have a possible result also in which we're showing the difference in gas versus the stellar dispersion in the center, which is a proxy for black hole mass. For all galaxies, we see nothing really happening, but if we focus only on the galaxies that are quenched or not forming stars, suddenly there is a correlation such that the more massive black holes at the center have lost more gas. So this could be a signature of AGNs removing gas and quenching the galaxies. And leave you the takeaways. The main takeaway for me is this works. We can extract the gas accretion history of galaxies. Maybe we can go to very high redshift because of the limitations of the method, but then we can just observe at higher redshift. But we can measure the amount of gas that is accreted in galaxies. And this is the QR code for the paper if you want. Thank you.
Thank you.
I only do what Benedetta tells me to do. So I have two questions. On one of them, you showed how the accretion rate over the stellar mass went negative, but you don't have outflows.
Yeah.
So how do you get negative that one, exactly that right-hand plot?
What we're doing is purely numerical. See, the code says, okay, this is the metallicity you should have. This is the metallicity we are predicted to have. Add gas until you match. So because we assume that we are here. If the opposite is happening, it's going to add negative gas, which has no physical meaning. But what it means here is that it's not, we don't need to dilute, we need to over-enrich. Which is what I said here is over-enrichment. What's happening here? Easiest answer is noise. These are the least massive galaxies. This is manga, and is the stellar spectrum. So I would not put lots of stock, but maybe what's happening is that because when you have outflows, you can have outflows of the richer gas, especially in the center, in which you dilute, because compared to the average of the galaxy, you're removing more metals than the average. But if you have outflows that are happening maybe on the outside, maybe like an outside down, outside in star formation, you might be removing gas that is less enriched than the average. This effectively would produce this. So I have a sort of a method answer and a physical answer. I don't know which one it is.
But this is kind of telling you about outflows, even though your model doesn't have outflows. Okay.
It could be physical, but it could also be noise. So I can't.
Thank you.
I would love it for it to be outflows because it's.
Thanks. This is really cool, and I guess that's related to what I was going to ask. I understand there is a lot of evidence from a number of different studies that the so-called metal loading factor of the outflows can be quite high, which touches exactly on what you said. And how could you possibly incorporate that into your model beyond what you told us at the end about looking at H1 to estimate the outflows? And the second question, you go through a lot of care, you said, to not use the instantaneous recycling approach when you deal with stellar mass winds, but it sounds like when you deal with galactic recycling, you are using an instantaneous recycling approach by just effectively lowering the mass loading factor from 2 to 3 to 0.6, assuming that it instantaneously falls back in.
That's not part of the model. That's just a calculation I do afterwards. It's not built in.
Oh, sure, okay. So then just about how you would incorporate outflows in the different metal loading factors.
Right now they're not incorporated. We're just doing sort of back of the envelope calculations to see if things make sense, which they appear to do. We want to include outflows, and then we have to include metal loading factors and stuff. I did do a little bit of calculation, and the metal loading factors that are in the literature, when I put not even the highest ones, just relatively high ones, I don't know, 1.5 or, I kind of, when I do this calculation, but I kind of run out of metals. If that is, without them falling back down and stuff, you can sustain a 1.5 or 2 or 2.5 metal loading factor and a mass loading factor of 2.5, because if you're above 1, you are removing more gas than the star formation, the stars you're forming, and you're removing more metals. You run out of metals. It can't be a steady state. It can be an instantaneous or biased by the point of observer, but you can't continuously remove more mass and more metals than there are, because you run out.
Thanks.
A very quick question while the next speaker comes in the back.
Hey, this is awesome. I was wondering whether the models and the data are good enough to make comparisons between accretion histories and star formation histories for individual galaxies, whether you see bursts of the star formation followed by accretion events and things like that.
Ooh, okay. I mean, I have to say, doing this, I already had to convince my supervisor that this was worth doing, because people who know about full spectral fitting say, this is way too much detail. I think that what we're getting is already because of one thing that I haven't had time to say, is that the templates of the spectra that we fit are taken with the same instrument as the data. And this removes a whole lot of the degeneracies, and it's what allows us to go here. That being said, what you want to do is probably going to be possible, because this is manga spectra. They have an R of 2000, is what they say. I would say more 1500. But with 10,000 R spectra, deep spectra, who knows what can be possible. So individual bursts, I wouldn't trust them, but we can get there.
Thank you. So the next speaker is Wilkinson, who will talk about the role of mergers in rapid quenching, a comprehensive analysis of post-starburst galaxies and merger detection.
Thank you. Hi, my name is Scott Wilkinson. I'm a graduate student at the University of Victoria, where I get to work with Sarah Ellison and all these lovely people. Most of my work focuses on how and why galaxies stop forming stars, and today I'll be talking specifically about the role that galaxy mergers play in the quenching process. So if you want to study a sample of galaxies that are rapidly quenching, a great way to do this is to look at a class of galaxies known as post-starburst galaxies, which, as their name suggests, have recently had a burst of star formation and then rapidly truncated all further star-forming activity. As is seen in their recreated star formation histories, these galaxies were on the star-forming main sequence, merrily forming their stars, had a burst of star formation, and have now recently quenched. And so the idea here is that these galaxies are caught in the process of stopping forming their stars. And if we can understand why these galaxies are stopping forming their stars, we can look at the causes of rapid quenching. So when we look to their optical imaging, we see that a great deal of these show signs of recent interactions and mergers. But when you actually go to try and quantify what fraction of post-starburst galaxies are caused by a recent merger, well, that has had a bit of a tumultuous history. So going back to 1996, Zablodoff et al. Studied a sample of 21 post-starburst galaxies and found about a quarter of them to be caused by recent mergers. And since then, we've had studies find as low as 4% of post-starburst galaxies to be caused by recent mergers, and as high as 60%, and just about everything in between. And so clearly, there's a lack of consensus as to what fraction of recently and rapidly quenched post-starburst galaxies are caused by mergers. And so a few things that we need to consider as to what might be, causing this effect is that there are multiple definitions of what it means to be a post-starburst. There are also multiple definitions of what it means to be a merger and how to identify those, including the quality of imaging they use to do so. And ideally, you'd have a large statistical sampling of post-starbursts and a control sample with which you can compare. Unfortunately, none of the previous studies have managed to hit all of those points, which is where my work comes in. To study post-starbursts, we use two different surveys. One, the Sloan Digital Sky Survey, which offers optical spectra with which we can identify the post-starbursts. And then a second survey called Unions, which offers deeper, higher resolution imaging with which we can identify the recent merger features more reliably. And it happens to have a large overlap with the northern portion of Sloan. And rather than run through the numbers of how much better the image quality is, I'll just show you an example of a post-starburst galaxy as viewed from SDSS, which looks something like this. And then that same post-starburst as viewed from Unions, which looks something like this, where the quality of imaging has now revealed that this post-starburst is very obviously a merger. From the overlap of these two surveys, we select two samples of post-starbursts, 157 classical E plus A post-starbursts and 533 PCA selected post-starbursts, both of which select post-starbursts on the basis of stellar, A-type stellar features in their optical spectra indicating recent star formation has occurred, but no nebular emission indicating that star formation has since ceased. The only difference being that PCA post-starbursts are a little bit more inclusive of things like AGN and shocks. When we look to quantify how many of them have been caused by mergers, we use a suite of merger identification methods, including non-parametric morphology statistics they might be familiar with, including asymmetry, outer asymmetry, shape asymmetry, Gini M20, all calculated using a Python package called StatMorph. We also use a deep learning convolutional neural network trained on simulated galaxy images in Bickley et al. 2021, as well as these samples just being small enough that we can classify them by eye, but that too comes with its own biases. So when we actually go to apply these merger identification methods to a sample of post-starbursts, it looks something like this. We get answers anywhere from 1 with asymmetry to 42% when I classify them by eye. So clearly, the merger identification method that's used to identify the mergers and post-starbursts has an effect on your results. But then if we use the same merger identification methods on a different sample of post-starbursts, here the PCA selected post-starbursts in blue, we again get completely different answers with the same merger identification methods, but a slightly different post-starburst selection. So again, it also depends on your post-starburst sample selection. Then lastly, even if we take the same post-starburst sample, the same merger identification methods, but change the quality of imaging, in this case using the Sloan imaging, we again get completely different answers, now systematically lower because the quality of imaging isn't quite as good. The good news is that regardless of your post-starburst selection, your quality of imaging, and your merger identification methods, the post-starburst samples generally have much higher rate of mergers than their star-forming controls, anywhere from 3 to 46 times more often to be mergers than their typical controls, demonstrating a clear causal connection between post-starburst, rapid quenched galaxies and recent mergers. But I don't know about you, I felt wholly unsatisfied with this slate of answers. You know, which of these solutions is correct? What is the actual merger fraction of post-starburst galaxies? And even if we had an answer here, if we picked, say, 30%, is it that the other 70% are caused by other quenching mechanisms entirely? Or is it that they're all caused by recent mergers, but that 70% are just being undetected for whatever reason as such? And so to answer that question, I looked at the Lustrous TNG 100 cosmological simulation, where I selected 424 recent mergers, synthetically imaged them as if they're at a redshift of 0.1, and it looks something like this idealized image here. If you then add observational realism, including sky noise, atmospheric blurring, it looks something like this in the worst quality imaging that we test. For reference, this is a little bit worse than SDSS in terms of both depth and resolution. And I'll put that up here. And then this is the highest quality imaging that we tested, which is a little bit better than the LSST 10-year stacks in terms of both depth and resolution. And then we can actually fill out the plane of image qualities all the way in between, where the worst quality of imaging is in the top left corner. From left to right, the images get deeper. From top to bottom, the images become higher resolution. And at each of these image qualities, we have 1,700 mergers, 1,700 non-mergers with which we can assess how effectively we're identifying recent mergers. And the results look something like this. So if you take the asymmetry statistic, for example, and apply it to that grid of images, in the worst quality imaging, we have precisely no mergers are detected as such, which improves as you increase the depth and resolution. But even in the best quality of imaging, we still only identify 42% of mergers as such, albeit also with increased false positives leading to low purities. The other non-parametric morphology statistics, when taken individually, are equally as bleak. So I'll skip to the positive result, which is that if you combine all the non-parametric morphology statistics together, train a random forest to do the classifications for you, you get better performance across the board, as good as 76% recovery, even in the worst quality of imaging, worse than SDSS, and as good as 86% recovery in the best quality imaging that we tested. Lower false positive rates across the board, leading to higher purity in your selected mergers. And so you can actually use these results to just correct for the merger fractions that you might have if your quality of imaging that you're using to identify mergers is somewhere in this grid. And as an example to do so, I'll show you what it looks like if you try and correct the post-starburst merger fractions that I showed earlier, which looks something like this. So the original results that I showed are on the left-hand side now, and now with the new x-axis. If you take two examples of the merger identification methods that I trust the most, you apply very generous correction, which is to say that we assume 100% of post-starbursts are mergers, and we just completely ignore false positives. We can scale this up. We can use the correction from our illustrious TNG results, and it gets us to about 80% of post-starbursts to be caused by recent mergers, and it still doesn't get us to 100%, indicating that while many post-starbursts have rapidly quenched in the local universe, not all of them have been caused by recent mergers. So that's all I have for you today. Thank you for having me, and I look forward to answering any questions you might have. Okay.
Yeah, I'll try to make the question. So, what is the typical environment of the galaxies?
Yeah, I've checked the environment of them, and either from the number of massive neighbors that they have and from halo, like estimates of their halo masses, these are very rarely in cluster environments, so they're mostly isolated.
Okay, because this also strongly depends on the environment. Clearly.
Absolutely, absolutely.
Yeah, I mean, in galaxy clusters, essentially all the post-starbursts come from ground pressure stripping, not
Agreed.
from merger.
Yeah.
And it's true that, most of the post-starbursts in number, they are in the field, of course, because there are more galaxies in the field. But the fraction of post-starburst depends linearly on the halo mass. So post-starbursts are much, much more frequent in clusters, and they are not mergers in clusters.
Agreed. Yeah. And also they depend on the stellar mass. If you check. Agreed. Agreed. Yeah. Absolutely depends on stellar mass. Yeah.
What direct evidence there is of classical E+A galaxies having suffered or experienced a starburst before being quenched?
Yes, this is almost wholly from, it was assumed for a long time, but I think
So it's a prejudice, not an evidence.
So the recent evidence, I would say, but not from my work, is the recreated star formation histories, which do show a burst. So if you do full spectral fitting, like prospector bagpipes, etc., the star formation histories that you do find do indicate a recent burst of star formation, and so their spectra do show a lot of recent blue stars.
Sort of similar question. Your Sloan spectra would also tell you something about AGN
Indeed.
Activity, and so do you see any patterns there?
Indeed. Yeah, so there are many of these do have AGN in their spectra. It doesn't get us to 100%, but there is an addition of AGN. Many of them do have AGN, but it's not enough to account for all the quenching mechanisms in there.
That's really interesting stuff.
Thank you.
Do you have cold gas, or molecular gas measurements, or H1, for a significant number of these, and to be able to say what the difference is with whether or not they're in a merger?
I'm so glad you asked. I'll get to that next. So no, there's...
I should ask you a coffee as well.
There have been recent, some small samples of post-starbursts that have, but surprisingly, actually, they have significant cold gas reservoirs. But we're limited to a very small sample size, and so we're looking to increase that sample size. I may have submitted some ALMA proposals, as well as we have an IRAM proposal that's been accepted, and it's in progress. That'll get unresolved molecular gas masses, but also paired with H1 masses as well. So that's in the works.
So let's thank Scott again. So the last speaker before the coffee break is Cignoni talking about star formation histories of the Milky Way, please.
Thank you. So, the goal of my talk is to show some results about the star formation history of the Milky Way, the local star formation history, using the latest Gaia release. Here is the volume we have analyzed, a cylinder with a radius 500 parsec and a vertical extension, vertical height of 1 kiloparsec. And so this study has been driven mainly by the lack of knowledge about the local star formation history. I mean, there are many results in the literature, even in the Gaia era, and they all differ a lot. So, what is the ideal sample of stars when we want to recover the history of a galaxy? Well, if we can resolve the stars in the galaxy, we want to reach the so-called oldest main sequence star-nova, so the position in main sequence of stars living more than one Hubble time. This means to reach basically the position of our sun. So in the G magnitude, in the Gaia magnitude is around 4 in absolute magnitude G. And we want a resolution, an error, photometric errors, parallax errors, of the order of 0.1 magnitude, at most 0.1 magnitude, which is roughly means 1 gigayear at 12 gigayear. Okay? With this sample, we can recover the star formation history of a galaxy over an Hubble time with a resolution of 1 gigayear at 12 gigayear. The Gaia errors are indeed, in this volume, are indeed very small. Here are the photometric errors. Here is the color error, and this is the G error. You see that 95% of the stars are errors of the order of hundreds of magnitudes or thousands of magnitudes. What is not negligible is the parallax error, and here is the distribution of magnitude errors due to the parallax precision, and you see that it's 95% of the stars have errors of the order of 500 of magnitudes, so hundreds of magnitudes. These errors are not negligible, so we take this into account to recover the star formation. How we recover the star formation? We use all stars inside the cylinder, plus minus 1 kiloparsec, and you can notice immediately it's an issue. The stars here are red clump stars, so stars are burning helium in their cores. The stars are 1, 2 solar masses, and they should be a clump. It's not a clump. You see this super elongated shape. This is basically differential extinction. So we have to correct star by star the extinction, and we use the latest maps, the 3D maps with a 10 parsec resolution by Vergely 2022, and they did a pretty good job. You see how much tighter is the CMD. There is still a contamination of extincted stars. So after some experiments, we found that the best way to clean the CMD was to remove all stars with an extinction higher than 0.25 magnitude. Unfortunately, with this selection, we lost many line of sights, in particular beyond 200, 300 parsec. So we have to restrict our analysis to a radial distance of 200 parsec. And with this selection, the CMD was much cleaner, and the residual extinction was negligible. So to recover the star formation, you use the synthetic CMD technique, and in particular the synthetic code Sfera, which is a classical synthetic CMD approach. This is the idea of a synthetic population. So we sample an initial mass function, we sample a star formation history, we sample an age-metallicity relation, we get masses, ages, and metallicities for the synthetic stars. We interpolate isochrons, so we have a fine grid of isochrons of stellar models. In particular, the core of our program uses the PISA stellar models. We add binaries, models of atmosphere, and we get the synthetic photometry in the Gaia filters. We break the star formation history into bursts with a different resolution. We have a contiguous burst which cover the entire Hubble time, and for each burst we have also a grid of metallicities. Our resolution in time is 50 million years now and 1 gigayear at 12 gigayear, so roughly 10-20% of the underlying age. And the metallicity, the metallicity resolution is 0.1 dex. There's an example of our synthetic models, which we use to compare to the observations, to the observation of CMD. We have, in the end, 27 age step and 15 metallicity step. The analysis is completely non-parametric, so we didn't assume any age metallicity relation. Well, to compare data with models, we have to, of course, to convolve models with all the errors we saw in the first slide, in the first slides, and we had to bin the CMD, to transform the CMD, the color magnitude diagram, into bidimensional histogram. So we used a binning of 0.1 magnitude in G and 0.05 magnitude in color. And we minimize the Poissonian K-square, and we use a genetic algorithm which is very robust to skip the local minimum and the bootstrap for the errors. And here is the regions we explored. This is an explosion of all the regions we explored up to plus minus 1 kiloparsec and the radius 200 parsec. Let's see the solution for the first, for the first volume, the closest, plus minus 100 parsec. This is the resolved star formation history as a function of time, present time, Hubble time, and what are the interesting features of this star formation. So a first announcement at about 10 gigayear, a long plateau, then the star formation rise again about 3 gigayear ago. There is probably a third announcement 1 gigayear ago, and the star formation is now at a lower level. There is a sort of lull in the recent star formation. Here is to see the quality of the reconstruction. Data, best reconstructed model corresponding to the previous star formation history, residuals in sigmas, and 95% of the residuals are below 2 sigma. Here is the red is an excess of data, green is an excess of models, model stars, or synthetic stars. There is only one significant difference, systematic difference, and it's the red clump. The red clump, the morphology of the red clump is quite different in this solution, in the best solution. Indeed, this is zoom in on the morphology of the red clump, so stars burning helium of 2 solar masses. So we decide to remove the red clump from the analysis. So this is just the star formation history without the red clump. The main feature, the first event is still there, the second event is still there, but we don't see anymore the two peaks at intermediate epochs. So the two peaks are probably an artifact of the red clump. And we still see the lull in the star formation activity in the last 500 million years. And, okay, in order to estimate a sort of systematics due to our assumed stellar models, we use a completely independent set of isochrons, set of models, the latest Padovan models. And the main difference is here at 3 gigayear. Overall, the broad features are the same. Lull rise at 10, 11, but also in the Padova solution there are not the two peaks, but the peak at 3 gigayear is happen earlier of about 1 gigayear. Okay, here is the solution for the Padova models, the best solution. The residuals are even better, in particular the red clump. Here is a zoom on the red clump. The morphology is well matched, and also the number of red clump stars is correct. So here is a comparison of the predicted age-metallicity relation for the solar neighborhood with Pisa and Padova. The two agrees quite well, considering that this is a purely photometric analysis. We don't use spectroscopy here. And you see that there is the only significant difference is where we have the largest discrepancies in the star formation history, in the range of 1-3 gigayear. This probably has to do, of course, with the underlying microphysics, probably the treatment over the overshooting. So this to the physics, to the specific models we use. However, the agreement is not too bad. And even better is the comparison with the observations. Here are the Pisa and the Padova solution, and the yellow histogram is just the observations inside exactly the same volume for which we derived the star formation, and from the apogee higher, so it's a high resolution spectroscopy. And so the agreement is pretty good. We have an excess of metal-rich stars of the order of 10%. And here is our solutions for all scale haze, okay? As expected, the recent star formation drops going higher and higher over the galactic plane. Up to 300 parsec, the yellow star formation, we still see the enhancement at 3 gigayear. So this must be something important in our galaxy, this event. But when we go beyond the 300 parsecs from the plane, I mean, the only significant feature, let's say, common feature is the enhancement at 10, 11 gigahertz, which is probably the formation of the thin disk or the thick disk. And we try to look at the radial dependence of the star formation history, and the result is that we don't find significant differences, except at very recent times. This is not unexpected. I mean, there's similarities going farther and farther from the sun on the plane, since we know that this is not the true star formation history. What we find is dynamically evolved star formation history. We know that radial migration exists, and so at this epoch we are covering a volume of 4 kiloparsec. Here we are covering a volume of 2 kiloparsec. I mean, sorry, on the plane we are covering 2 kiloparsec, 4 kiloparsec. And if we compare our results with the literature, we found a nice agreement with the two results. Bernard and Moore, who analyzed the first one is a similar volume, this is a larger volume. Overall, we find the same enhancement at 3 gigahertz. At early times, here it's quite uncertain, so it's difficult to compare with our result. This is a very recent result, high resolution result based on a similar technique, so a synthetic CMD technique, and also this result we see the enhancement at 3 gigahertz, and also the beginning of star formation in the disk, which is close to 10 gigahertz. Other studies based on Gaia data are difficult to compare with our results since the resolution is quite lower. However, the 3 gigahertz event probably is visible also in these solutions. So here is the summary of this analysis. The star formation history of our galaxy is definitely not constant. Okay, there is probably an enhancement 10, 11 gigahertz ago. Then there is a long plateau, an enhancement 3, 4 gigahertz ago, depending on the model, and a lulling activity at recent time. The age metallization we find is quite tight, and we don't find a radial dependence on the star formation, at least up to 500 parsecs. So we don't know what is the culprit of this enhancement. So this is just a smoking gun or something. So this is something for modelers. Thank you.
Hi, this is very interesting, thank you. I have two questions, both about the early evolution.
Yes.
So first, is it possible to go deeper to the center, because early on the galaxy was smaller, so most of the stars that formed early on they're in the center, right? So whether it's possible to go beyond 500 parsecs.
So you mean to
go to the center, like closer to the center. Maybe not in the disk plane, but off plane where you can still
to
see.
the center, meaning to the galactic center?
Yeah.
Okay. I mean, using this kind of data?
Yes.
No, at the moment it's not possible. The reason is the extinction, no? I mean, what we can do is, okay, we do not study the disk, but we study something higher. On
yeah, exactly. Yeah.
That's it. Yeah.
Yeah.
Yes. Yes, probably above 300 parsec. Probably yes. We can do it.
And another related thing is, so you showed that if you go high above the plane, you start seeing a bump at early times. Now, do you apply any kind of cuts in situ versus accreted population? Because, yeah, some of these stars can be from the halo, right? So they can be brought up.
Well, not from the halo. The halo is a matter fraction within 1 kiloparsec. It's a thick disk,
probably. At kiloparsec heights.
Yes, no, we didn't apply any selection. No.
Okay, thank you.
Very nice. Strictly speaking, the evidence is local for an enhancement. What clues may we have whether this enhancement is global? Or do we have evidence that this may be local?
We don't know. We don't have an evidence that it's yes.
Just read there.
Yes.
Also the Large Magellanic Cloud and the small.
But the culprit of this enhancement is probably or the LMC or the Sagittarius. Okay, I'm not aware of other galaxies which are, playing with our galaxies in so many giga-year. But according to the kinematical models, the Magellanic clouds are at their first infall. So the remaining culprit should be Sagittarius of this enhancement.
What is the amount fraction of stars that were formed during this burst? Is it a good fraction of the whole stars that you see?
The burst at 3 giga-year? Yeah. Yes, so let's say at 300 parsec, at 200 parsec, later than the burst, 40%.
Okay.
Okay, at the burst in 1 giga-year, 5%.
Exactly. Yeah, it was always to understand if it is a local episode of a burst of star formation or accretion of a different population that
the real problem
the
is
amount
the
of stars
dynamical evolution. So
okay.
The scattering of orbits.
It would
so
scatter
it's
away.
difficult to because at 10 giga-year it's not local, of course, what we find. At 3 giga-year, yes, it's representative of a 3 kiloparsec volume. So,
well, I think it's time for interrupt. We have just a couple of announcements, just first, thanks to Kevin. People who didn't manage to register, they can register now, and people presenting a poster this afternoon and haven't yet uploaded the slides, please do so. And even though you're doing on Thursday and you haven't done it yet, please do it so. And we reconvene in half an hour, 11:35. Thanks.